Okay, so we're on chapter 3 of Further Mechanics 2, and it's centres of maths still. It's just called Further Centres of Maths because it's the A2 content, and basically this just starts taking you through calculus and 3D solids that we might have. So like I've said here, this chapter continues with the same concepts as chapter 2, but it explores the use of calculus for non-standard shapes of laminae as well as for 3D bodies. So we've got these 3D here just to remind us this one's going to cover 3D. Now the remaining chapters, so chapter 3, 4 and 5 of Further Mechanics 2, they're very integration heavy, and be warned that all skills of integration from pure and core pure can be tested in the exams. Although most of the examples that we're going to be doing in this chapter and in this booklet are pretty straightforward integration, but you might need some of the integration later on when you're doing the exams. It's a bit more challenging. So I've got some prerequisite knowledge here so that you know if you haven't done these things, it's probably not a good idea to try and start this one. First of all, I think you really should have done integration from pure year 1 and pure year 2 of normal maths. You also need to have done volumes of revolution from core pure year 1, which I imagine you would be if you're doing this A2 chapter from Further Mechanics 2. And you definitely need forces and friction from mechanics year 2, but you've probably covered most of that if you've done some of the stuff from Further Mechanics 1 with like work, energy, power and things like that. It's useful to have some stuff about polar coordinates from core pure year 2. We'll be using polar coordinates just for a couple of examples here to do some proofs. And then last of all, it's important that you've maybe done moments. Some of the concepts of moments from mechanics year 2 are going to get used in this, and I think we've got an exam question later on where we will be using almost exactly the same style of stuff from year 2. So we're going to cover, in the first exercise, we're going to just be doing 2D shapes using calculus. We'll then learn about 3D bodies, some of them with calculus and some of them without. We'll then be learning about non-uniform bodies, where maybe the mass or the density varies. And then we're going to be thinking, like we did in chapter 2, what happens when they're in equilibrium. And then toppling and sliding is to do with particles, or not particles, but bodies on slopes, and whether they will slide down the slope or whether they will sort of rotate and turn over. And as usual, we'll do a few exam questions at the end of this. Okay, so let's get started by thinking about the centres of mass for 2D bodies using calculus. So 2D laminae we're going to be thinking about right at this point. We're going to build a formula to find the centre of mass of a lamina using calculus, and we'll use the same concept as before. And that same concept of before was the sum of the moments of the particle's weight is equal to the moment of the total weight at the centre of mass. So what we're going to do to begin with is, this is the lamina that we're looking at. We're looking at it between A, the x-axis, B, and the curve Y. We're looking for this sort of lamina that we've got here. So I guess I could just highlight this is the part that we're actually looking to find the centre of mass for. Well, this is probably the part we might deal with first of all. We're going to find the moment of the total weight at the centre of mass. So first of all, I guess we need to find out the mass of the lamina. So we're going to think about how we would find the mass of the lamina. Now we're just going to presume that it's going to be like a constant kind of a uniform sort of mass, that it's distributed evenly. So actually the mass of the lamina we're just going to say is equal to the area of the lamina. And we know that the area of this lamina is just going to be when you integrate this curve between A and B. So we're going to be integrating Y with respect to X between A and B. We're going to be integrating Y with respect to X in terms between A and B, and sometimes we give this a capital letter M to say that that's what that part is. So this moment of the total weight, the moment is just going to be equal to x bar M, which is x bar, the integral between A and B of y dx. Now this is the part we're going to think of where we're finding the sum of the moments of the particle's weight. Now we might not say weight, we could also be thinking to ourselves here, instead of weight, we know that we can just talk about these things as mass or even as area because of the fact that we're talking about something in 2D. We're always interested in like the mass ratios. It doesn't have to be the weight because obviously the weight's just going to add g into all of those bits. So now what we're going to do is we're going to have a look at an individual strip. So let's look at an individual strip. Well, the first thing that we're going to need to do is to find the mass of a strip, which is the same thing as the area of a strip. And we know that the area of one of these strips, and I'm talking about this little rectangle that we've got here, it is dx along the bottom multiplied by its height, which is y. So the area is y dx. okay, because it is a rectangle that looks like this. The height is y and the base is dx. So now what we'll do is we will do a moment of one strip. Well, the moment of one strip would be the mass, which is y dx, and we would multiply it by, we're going to just be talking about the x at this point, we would multiply it by the location of the centre of mass in terms of x. Now the centre of mass of it's going to be here, and if this is x, because that's the first part of it, the centre of mass, as this gets infinitesimally small, the centre of mass will just be at x. So it's going to be y dx multiplied by x. So in other words, it is x, y dx. So the sum of the moments, and I'm saying this is for my x coordinate, the sum of the moments is therefore going to be, when you add up all of these x, y, dx's, which is this, we know that this integration means to sum up, and we're summing up all of those x, y's, dx between a and b. So we've now come up with what the x bar thing is going to be. It's this part that we have here. It's this must be equal to this. So I'm just going to write that down. We now have that x bar, the integral of a between a and b of y dx, must be equal to the sum of these moments. Remember, this means the sum of. So we're adding up all of the x, y, dx between a and b. Now what we're going to do is just have a think about what is the moment of one strip in the y direction. So if we're doing it in the y direction, the moment of one strip is still going to be the area, which is y dx, but we're going to think about what would the coordinate be of the centre of mass. Well, we said that the coordinate of the centre of mass would be x, because as this gets really thin, it will just be x, but this is in the middle of this strip that we've got here, and the height of this strip, we know the height of this strip is y, so we know that this part from the top to the bottom for the centre of mass is going to be a half of that. It'll be half the way up, so it's going to be multiplied by a half y. In other words, it is not the integration symbol yet, it is a half y squared dx. So the sum is just going to be equal to, between a and b, a half y squared dx. In other words, we get that y bar, ab y dx, so we're now talking about the y coordinates, would be equal to a half between a and b of y squared dx. So these are the formulae that we've got. I'll just quickly highlight this so you can see which one I'm saying is the same. This one is the same as this one. It helps you find the x coordinate. And then this one that I've written down here is obviously the same as this one here, and it will help you find the y coordinate of the centre of mass. Obviously x bar and y bar are those coordinates. And you might see it in this kind of alternative form like this. This thing that we've got here was the mass. This thing that we've got here was the mass. So really the change is that for the x one, it's being multiplied by x. And for the y one, it's being multiplied by a half y. The reason it gets multiplied by x is because its location is at x, and the reason it gets multiplied by a half y is because the centre of mass's y coordinate is at a half y. So they're pretty similar to how you'd expect them to be. Even if you can't memorize them, they kind of make logical sense about where they should come from. Obviously, it's just going to be some integration that goes on in here. And when you do this integration, you cannot do it on your calculator. You do have to show them that you've done the integration. And I would even want you to show the substitution into the limits, just to make sure that you are getting all of those marks. And they often say that at the start of some questions. So I'm going to do a couple of examples that we've got here, and then we will do some standard results that we might have here. So we're going to find the coordinates of the centre of mass of the uniform lamina bounded by the curve with equation y equals 4 minus x squared, the x-axis and the y-axis. So 4 minus x squared, you should know what this looks like. It looks like this. But we only want it bound between the x-axis, the y-axis. So actually I don't need this branch at all. So I'm just actually interested in what does this lamina have as its centre of mass. Now, because it's y equals 4 minus x squared, this is clearly going to be a 4. And then along the bottom that we have here, we're going to be making that equal to 0. So it would be x squared equals 4, x is equal to 2. Okay? So using the formula that we've got here, we're going to need to build up a few different things. Our formula is x bar, the integral of a b y dx, is equal to, for the x coordinate, is going to be xy dx between a, b. And then we'll do our y1 is going to be same thing. Apart from it's going to be a half y squared dx between a and b. So we've got a few different things that we need to find out. I think the first thing we're going to do is we're going to integrate y with respect to x between 0 and 2, because that will tick off these things. So I'm just going to say this one and this one is this part that we're doing right here. So I'm going to do some very speedy integration because I'm not teaching you integration here. We're just going to get 4x minus a third x cubed, and that is between 0 and 2. So when I sub in the 2, I'm going to get 8, and then when I sub in 2 to the next part, I'm going to get minus 8 thirds. So I will do 8 minus 8 thirds. No point in doing the 0 because that's just going to go. So that is 16 thirds. Now my next one that I'm going to do, I will do the xy dx. So I'm now going to be integrating x multiplied by 4 minus x squared dx between 0 and 2. So that's integrating 4x minus x cubed dx between 0 and 2. So that is 2x squared minus a quarter x to the power of 4 between 0 and 2. So subbing in 2, that is going to be 2 times 2 squared, that's 8, minus a quarter times 2 to the power of 4, which is 4. So that one is just equal to 4. So there is the blue part that I was working out. I'm going to do the last one, which is my half y squared dx. So I'll probably see if I can fit this in here. So I'm going to do my half. Now my y squared is going to be 4 minus x all squared. 4 minus x squared, sorry, all squared. And that's between 0 and 2. So I'm going to expand the brackets on this to be able to actually allow me to do the integration. So it's going to be a half. It's going to be 16 minus 8x squared plus x to the power of 4 dx between 0 and 2. So it is 16x minus 8 thirds x cubed plus 1/5 x to the 4 between 0 and 2. So that's going to be a half multiplied by 32 minus 64 over 3 plus 16 over 5. It's just me doing a lot of substitution in my head. So let's just quickly do that. 32 minus 64 over 3 plus 16 over 5. I'll also half that, and we get that it is 104 over 15. Now, I wasn't sure if I was going to need an extra page. I am going to need one, so I'm just going to quickly drag one from the bottom that I've got here as a spare, if it will let me. Okay. So now that I've worked out all of those different parts, I'm actually just going to do the divisions to actually come up with the things that I'm looking for. So x bar is going to be the blue answer divided by the yellow answer. So I can now say that my x bar is going to be my 4 divided by my 16 over 3. So that is 12 over 16, or 3 over 4. So that's my location for x bar. And then y bar is also the green part divided by the yellow part. So it's 104 over 15 divided by 16 over 3. So that's 104 over 15 divided by 16 over 3. Which is 13 over 10 that we've got for that part. So that's 13 over 10, which I think, have I made a mistake in that part? Yeah, I've probably made a mistake in this. Let me just double check if I've done this integration correct. So that was, yeah, I didn't do the substitution correctly. I didn't integrate this correctly. I've done it as a 5th x to the 4. I hope you were screaming at me. This should not have been to the power of 4. It should have been to the power of 5, which is going to change everything. So that should have been to the power of 5, which means this should have been 32 over 5. So 32 minus 64 over 3 plus 32 over 5. It is 256 over 15 divided by 2. It should have been 128 over 15. My apologies. So this is 128 over 15, which changes my final answer to 8 over 5. So our coordinates of the centre of mass are 3/4 and 8/5. Okay? So let's now try a different question where we're going to have to be a little bit more careful about the way that we use our formulae and how we might adjust the way that they're going to look. So it says find the coordinates of the centre of mass of the uniform lamina bounded by the curve with equation y equals root x and the straight line with equation y equals half x. So I'm going to begin by doing a sketch of what is going on here. Now y equals root x we know is this kind of shape, and then y equals a half x is going to be a straight line that looks like this. So the thing that we're interested in is we want to find the centre of mass of that lamina that we've got there. Obviously, these two branches that we've got here are not going to be very useful. I think probably the first thing that I want to do is find out what that axis or what that intersection point is going to be. So we're going to make the square root of x just equal to a half x. I'm going to square both sides so that x is equal to 1/4 x squared. Now you shouldn't normally divide by x, but I will divide by x in this case just because I'm wanting to find the positive solution. So I get 1 equals 1/4 x. In other words, x is equal to 4 in this part. So I know I'm going to be doing the integration between 0 and 4. Now let's just think really carefully about what this is going to look like, because normally when we're trying to find integration between two curves, we do the top curve minus the bottom curve that we've got here. So if I call this top one, if I say that this is y1 and that the one underneath it is y2, when we're going to try and find out what the area is, we normally would find out the area, which I'm just saying is kind of like the mass. We would normally integrate it between 0 and 4 of doing the top curve minus the bottom curve, and we would do that with respect to x. So that part is going to be perfectly fine in our formula. However, we need to be careful about when we do the y bar and the x bar parts. So if we imagine that we took a little strip of one of these parts, the x part is still going to be at the x location. So when I'm going to do the formula for x bar, it will be, let's do this in blue, it will be mx bar equals this part multiplied by x dx between 0 and 4. But when I do the y part, I want you to think really carefully about how you're going to find this, because previously we just said it's going to be a half of the y coordinate. Well, is it going to be a half of this y coordinate? Is it going to be a half of this y coordinate? I want to know what is the location of the middle of one strip. Well, to find the middle of that one strip, you're actually finding the average of these two. You're going to add them together and you're going to half it to find that part. So this is actually the average of y1 and y2 added together. If we subtracted them, we would find the gap between them, but if we halved it, it would actually be finding something down here. So fundamentally, we need it to be in between them, which is why we add them and divide it by 2. We're finding the midpoint of those bits. So when we do the part for y, my bar is actually going to be equal to, between 0 and 4, there's going to be the half that still comes out the front, but there's going to be a y1 plus y2. That's because of this thing that we've got here, and that's going to be multiplied by y1 minus y2 dx that we've got here. So there's a few different parts that we're going to need to work out for this, and for those different parts, I'm going to definitely get myself an extra page from the bottom here, because there's going to need to be quite a lot of integration calculations. So although those formulae that I gave you at the beginning, although those formulae are kind of like something that you should memorize, it's more important that you understand really like where they come from and how you might be able to adapt them and build them yourself, okay? So I'm going to begin by working out all of these different things that we've got. I'll start off by doing this one that's in here, and then we'll go through them, okay? So I'm going to integrate between 0 and 4 of y1 minus y2. So y1 is this one, and this one is y2. So that's integrating x to the power of a half, square root of x, minus a half x with respect to x, between 0 and 4. So I'm going to increase that power and divide by that new power, so that's 2/3 x to the 3 over 2, minus 1/4 x squared, and that is between 0 and 4. So I only need to substitute in the 4 to this. So when I substitute in the 4 to the power of 1.5 times 2/3, that's 16/3, minus 4 squared divided by 4 is 4. So that's 16/3 minus 4. That is 4/3 for the part that we've got in yellow there. Now, obviously, you won't be able to use yellow and stuff when you're doing the exams, but even if you put like a box around them or something, that will usually be more helpful. So now I will do this blue part. That's going to be integrating between 0 and 4 of y1 minus y2 multiplied by x. So I'm going to multiply this, which is y1 minus 2. I'm going to times it all by x. So that is going to be, I'll do it a little bit slower. So I'll do x to the half minus a half x with respect to x. So between 0 and 4, that is x to the power of 3 over 2 minus a half x squared dx. So that is going to be x to the 5 over 2 multiplied by 2/5 minus a 6th x cubed between 0 and 4. So I'm only bothered about subbing in the 4 here. So 4 to the power of 5 over 2 times 2/5, that's 64 over 5, minus 4 cubed divided by 6, which is 32 over 3. And we get 32 over 15. And this was the stuff that I was doing for the blue calculation. Now I am going to do my yellow calculation, which is probably the one that's going to take a bit longer because I'm going to need to do some expanding of the brackets. So my green, did I say yellow? I mean green, between 0 and 4. So I'll do my y1 plus y2, which is my x to the half plus a half x multiplied by x to the half minus a half x. I'm hoping you're noticing there's a difference of 2 squares there. So I actually only need to multiply those two and multiply those two. So x to the half times x to the half is just x to the 1. And I'm going to be subtracting a half x times a half x, which is minus a quarter x squared with respect to x. So that is a half x squared minus a 12th x cubed between 0 and 4 when we do the integration. So that is going to be a half x squared. A half times 4 squared, that is 8. And I'm going to be subtracting a 12th of 4 cubed. So that's 64 over 12 or 16 over 3. I've got my calculator with me. And that all then becomes 8 over 3. So the green part that we've got was all of this and has this answer. So I can now go and actually say what my x bar is going to be equal to. So the x bar is going to be the blue divided by the yellow. So x bar is the blue answer, 32 over 15, divided by the mass, which is 4 over 3. So 32 over 15 divided by that, and we get 8/5. And then the y bar will be, from our y bar formula, be the green divided by the yellow. So that's going to be 8/3 divided by 4/3, which is just 8 over 4, or just 2. So our centre of mass here, our centre of mass is 8/5 and 2 for this particular question. Have I done that bit right? I now think I've perhaps made another mistake. Oh, I know what my mistake was. I knew there was a mistake, and I'm hoping again you were screaming at me. I didn't copy down the half. I did not copy down that half. So there needed to be a half here, a half here, a half here, and a half here. 2 mistakes. Everyone makes mistakes. It's good to keep these things in, I think. So actually that's a 4/3, which means this is just a 4/3 over 4/3, so it's just a 1. 4/3 over 4/3, so it's just a 1, so it's 8/5 and a 1. I'm trying to think if I could have known that the 2 was completely wrong for the y coordinate. I mean, if it's crossing at a 4 here, then this is a 2. Yeah, I guess I should have known that if x is 4 here, this top part of the graph is 2. So it doesn't make sense that the centre of mass could have had a 2 for y. It makes sense that the centre of mass has to be lower than that. So although I've borrowed this example from the textbook so I could see, I knew I'd got this wrong, I could have reasoned with myself and said, okay, well, 1 doesn't make any sense. How could it be a 1 when the graph only goes up to a 2? So just kind of like building up the formula in all of these different ways is going to be the most useful kind of approach to these kinds of questions, and just kind of laying your work out in the way that I've done, hopefully doing a better job of me of remembering that that half needs to be there. So in the next video, we're going to do some proofs of some of the standard shapes that we already know about. We're going to prove their centres of mass.